Imagine you're inside a giant soap bubble, but you can't see its edges. How would you figure out if you're in a sphere, a cylinder, or maybe a completely flat shape that stretches infinitely? Now, multiply that bubble by 93 billion light-years in diameter, and you've got one of cosmology's most fundamental questions. What's the true shape of our universe? The answer to that question doesn't just define where we live, it also reveals the ultimate fate of everything that exists. In this video, we go in to uncover how scientists measured the geometry of the cosmos using the universe's oldest radiation, and why this discovery forever changed our understanding of the future of all galaxies, stars, and planets. Hey there, cosmic explorers. Welcome back to Cosmic Frontiers, where we unravel the universe's mysteries together. We're a community growing every day on our journey towards 1,000 subscribers. And today, we're diving into one of modern astronomy's most extraordinary discoveries. For millennia, humans have gazed at the night sky and wondered about the nature of the space around us. Does the universe curve in on itself like a giant sphere? Does it stretch infinitely like a flat sheet? Or perhaps it has an even stranger shape? To grasp this question, we first need to understand that we're talking about something far more profound than just the shape of things in space. We're talking about the very geometry of the fabric of spacetime itself. Einstein taught us that space isn't just an empty stage where things happen. Space itself can be curved by the presence of matter and energy. Imagine a tightly stretched trampoline that's a good representation of flat space. Now, place a bowling ball in the center. The trampoline curves, creating a dip. If you roll a marble near the bowling ball, it'll follow a curved path, as if drawn in by the larger ball. This is exactly how gravity works in the universe. Masses curve space-time, and this curvature is what we perceive as gravitational force. But here's the fascinating question. If we look at the universe as a whole, what's the overall curvature of space? Cosmologists have identified three main possibilities, each with dramatic implications for cosmic destiny. The first possibility is a closed universe. Imagine the surface of a sphere. If you start walking in a straight line in any direction, you'll eventually return to your starting point. In a closed universe, space curves in on itself in a similar fashion. If you could travel in a straight line for long enough, you'd theoretically come back to your origin. Geometrically, this type of universe has positive curvature, like the surface of a ball. The most striking characteristic of a closed universe is that it contains enough matter and energy density for its own gravity to eventually halt its expansion and cause it to collapse in on itself in a catastrophic event called the Big Crunch. The second possibility is an open universe. Think of the shape of a horse saddle, curved upwards in one direction and downwards in another. This type of geometry has negative curvature. In an open universe, parallel lines diverge from each other as they extend. This universe doesn't have enough density to stop its expansion, so it will continue expanding forever, becoming increasingly colder and emptier until all stars burn out and only black holes remain, slowly evaporating through Hawking radiation. The third possibility is a flat universe. Here, we return to our perfectly stretched trampoline analogy. In a flat universe, the Euclidean geometry we learned in school works perfectly. Parallel lines remain parallel, and the sum of the angles in a triangle is exactly 180 degrees. A flat universe is precisely at the boundary between closing and opening. It has just enough critical density for its expansion to gradually slow down, but never completely stop. Now comes the trillion-dollar question. How on earth do we measure the shape of something as vast as the universe? The answer came from one of modern astronomy's most elegant discoveries, involving the oldest light we can observe. In the first 380,000 years after the Big Bang, the universe was opaque, filled with a hot plasma of protons, electrons, and photons. It was like trying to see through a dense fog. But when the universe cooled enough, something extraordinary happened. Electrons and protons combined to form neutral hydrogen atoms, and suddenly the universe became transparent. The photons that were constantly being scattered were finally released to travel freely through space. This primordial light still exists today, but stretched by the universe's expansion from visible light to microwaves. We call this the cosmic microwave background radiation, or CMB. The CMB is like a photograph of the baby universe, a snapshot of how things were when the cosmos was just 380,000 years old. And here's the ingenious trick. The tiny temperature variations in this radiation carry information about the geometry of space. It's as if the young universe left its fingerprint etched into the oldest light that exists. To understand how this works, imagine you're observing sound waves in a room. If the room is small and enclosed, the waves will behave in a specific way, creating characteristic interference patterns. If the room is very large or has a different shape, the patterns will be different. Similarly, fluctuations in the density of the primordial universe created sound waves, literally pressure waves, propagating through the cosmic plasma. The geometry of space determined how these waves behaved, and when the universe became transparent, these waves were frozen into the temperature patterns of the CMB. In 1989, NASA launched the COBE satellite, which made the first precise measurements of the CMB. The results were revolutionary, confirming not only that the radiation existed, but also revealing the minuscule temperature fluctuations that would be the seeds of future galaxies. But COBE was just the beginning. In 2001, the WMAP satellite was launched, mapping the CMB with much higher resolution. And then, in 2009, came Planck, an extraordinarily precise machine that measured the CMB with unprecedented detail. What these experiments discovered fundamentally changed our understanding of the universe. The data showed something surprising. The universe is extraordinarily flat. When scientists analyzed the patterns in the CMB, they found that the geometry of space almost perfectly matches a flat universe, with a margin of error of less than 1%. It's as if nature used a perfect cosmic ruler to create the cosmos. But here's the mystery. Why is the universe so perfectly flat? This is a profound question because, of all possible geometries, flatness is extremely special. Imagine trying to balance a pencil on its tip. There are infinite ways for it to fall, but only one way for it to remain perfectly balanced. Similarly, there are infinite ways for the universe to be curved, but only one way for it to be flat. The answer might lie in a theory called cosmic inflation. In the first moments after the Big Bang, we read talking about the first 102.32 seconds. The universe might have undergone a period of extremely rapid, exponential expansion. During inflation, any initial curvature would have been stretched out, until it became negligible. Just as the surface of a balloon appears flat when you're very close to it. This is one of the most elegant predictions of inflation theory. And the fact that we observe a flat universe is one of the strongest pieces of evidence that something like inflation truly happened. But let's talk about what this flatness means for the universe's fate. In a flat universe, expansion will continue forever, but at an increasingly slower rate. Galaxies will drift apart, stars will eventually burn out, and the universe will become an increasingly colder and emptier place. But this process will take trillions upon trillions of years. We read talking about timescales that make the universe's current age, 13.8 billion years, seem like a blink of an eye. There's yet another fascinating complication: dark energy. The most recent observations suggest that the universe's expansion isn't just continuing, it's accelerating. This indicates the presence of something scientists call dark energy, a mysterious force that accounts for about 68% of all energy in the universe. If dark energy remains constant, the future could be even more dramatic, with accelerated expansion eventually tearing apart all cosmic structures. The Planck satellite's work also revealed other fascinating secrets. The detailed CMB maps allowed us to measure the universe's composition with extraordinary precision. Only 5% is normal matter, the matter we're made of. 27% is mysterious dark matter, and 68% is even more mysterious dark energy. It's humbling to realize that we directly understand only 5% of the universe. The patterns in the CMB also tell us about the first structures that formed in the cosmos. The slightly denser regions became the seeds of future galaxies and galaxy clusters. It's extraordinary to think that we can trace the origin of the Milky Way back to a microscopic quantum fluctuation in the primordial universe. But perhaps the most profound aspect of this discovery is what it reveals about the fundamental nature of reality. The fact that we can measure the geometry of the universe using light from 13.8 billion years ago demonstrates the elegance and consistency of physical laws. The same equations that describe how an apple falls from a tree also govern the evolution of the entire cosmos. It's important to mention that our current understanding is based on the standard cosmological model, also known as the lambda CDM model. This model has been extraordinarily successful in explaining a vast range of observations, from the CMB to the formation of large-scale structures. But science is always evolving, and future observations might reveal surprises. The coming years promise even more exciting discoveries. New telescopes, like the James Webb, are observing the first galaxies that formed after the cosmic dark ages. Future experiments might detect the primordial gravitational waves left by inflation, providing even more direct evidence about the universe's earliest moments. So, what have we learned about the universe's shape? We've discovered that we live in an extraordinarily flat cosmos, almost perfectly balanced at the boundary between collapse and eternal expansion. This flatness is unaccidental, it's likely the result of a period of cosmic inflation that stretched out any initial curvature until it became imperceptible. The flat geometry of the universe suggests a future of eternal expansion, where galaxies will gradually drift apart until the cosmos becomes a cold and empty place. But this will take trillions of years, longer than our minds can truly grasp. The most fascinating part is that we managed to figure all this out by analyzing the light patterns left behind when the universe was just a cosmic baby. It's one of human science's most extraordinary achievements, using our curiosity, creativity, and technology to unravel the secrets of reality on its grandest scale. When I look at these discoveries, I'm impressed not just by what we've learned about the universe, but by what it reveals about ourselves. We are a species that evolved on a small rocky planet, yet we've developed the capacity to understand the geometry of the entire cosmos. In a sense, we are the way the universe came to know itself. Cosmic explorers. This leads us to a profound reflection. If the universe is truly flat and will expand forever, does that make our existence less significant or more precious? I believe it makes everything even more extraordinary. In a vast and largely empty cosmos, the emergence of life, consciousness, and scientific curiosity is an improbable and beautiful miracle. Now I want to hear from you. What do you find most fascinating about the discovery that the universe is flat? Is it the extraordinary precision of the measurements, the connection to cosmic inflation, or perhaps the implications for the distant future? Leave your thoughts in the comments. I love reading your perspectives on these cosmic mysteries. And cosmic explorers, what universe mystery do you want me to talk about in the next video? Primordial black holes, the nature of dark matter, the multiverses. Leave your suggestions in the comments. We're on an incredible journey towards 1,000 cosmic explorers. If this video expanded your horizons about the fundamental nature of reality, join our crew by clicking subscribe. Like this video if it sparked your curiosity about the cosmos' geometry, and share it with someone else who also marvels at the universe's mysteries. In the next video, we'll explore another fascinating enigma, how the universe's first stars differed from everything we see today, and how they forged the chemical elements that made life possible. Until then, keep looking up and wondering about the marvels that surround us.